There is a canyon in southwest China so deep that clouds form inside it. Winds rip through it with enough force to tear equipment off a cable. The rock walls are unstable limestone that crumbles unpredictably. The river at the bottom sits 625 meters below the rim, taller than any building in the United States except one. For generations, the communities on either side of this canyon were separated by a 2-hour journey through treacherous mountain roads. One wrong turn, one patch of ice, one mechanical failure on those roads, and there was no recovery. China's answer was to stop going around the canyon and start going over it. The Huajiang Grand Canyon Bridge is now the highest bridge on Earth. It costs $300 million. It stretches 2,890 meters long, with a central span of 1,420 meters. It sits 625 meters above the river below, and it cuts that 2-hour mountain journey down to 2 minutes. Building it required solving engineering problems that had never been solved before. Here is exactly how they did it. The problem with building over a canyon this deep. Most major bridge projects deal with water. Rivers, bays, ocean crossings. The challenge is spanning the gap and managing the water beneath. Engineers have centuries of experience with that. The Huajiang Canyon is a different category of problem entirely. The canyon walls are not solid rock. They are limestone, a material that looks stable from the outside and can be completely unpredictable underneath. Limestone is porous. It fractures in unexpected directions. It dissolves over time when water moves through it. You cannot simply bolt an anchor into limestone and trust it the way you would granite or sandstone. The rock might hold for a decade and then shift. The canyon also creates its own wind system. Hot air rising from the river at the bottom collides with cooler mountain air at the rim, generating violent updrafts that are almost impossible to predict. Winds change direction without warning. Gusts hit with enough force to send equipment swinging dangerously on cables hundreds of meters in the air. And the two sides of the canyon are not symmetrical. The north wall and south wall have completely different geological compositions, different rock types, different fracture patterns, different load-bearing capacities. A standard anchoring approach that works on one side would fail on the other. Every single one of these problems had to be solved before 1 meter of bridge could be built. Carving foundations out of sheer cliffs. The bridge anchors are the most critical part of any suspension bridge. They are what the main cables connect to. Every ton of load on the deck, every car, every truck, every wind force pushing against the structure, all of it travels through the cables and into the anchors. If an anchor moves even slightly, the entire bridge moves with it. On the north side, engineers used controlled explosions to carve a massive shelf directly out of the canyon wall. Then they poured a gravity-based concrete anchor, a structure so heavy that its own weight holds the cables in place. The sheer mass of the concrete resisting the pull of the cables keeps everything locked. The south side required a completely different solution. The rock there was steeper and more fragmented, too unstable to support a surface anchor of any kind. So engineers bored a deep tunnel directly into the core of the mountain and grafted the anchor inside the rock itself. Instead of sitting on the canyon wall, the south anchor is buried inside it, using the mountain's own internal structure as the holding force. 2 anchors on the same bridge, using 2 completely different engineering principles, because the canyon demanded it. Building towers at the edge of the abyss. With anchors secured, the next step was erecting the 2 main towers that would carry the suspension cables across the 420-meter gap. The north tower stands 262 meters tall. The south tower stands 205 meters. Both rise from the very edge of the canyon rim, narrow ledges of rock with a sheer drop on one side and mountain terrain on the other. Construction crews used massive tower cranes, including the ultra-heavy Potain MiC 385, to build the towers section by section. But the humidity inside the canyon created another problem. Standard concrete does not cure properly in high-moisture mountain environments. It weakens. It develops microfractures that are invisible on the surface, but compromised structural integrity over decades. Engineers developed a specialized eco-friendly concrete mix specifically for this project, formulated to harden correctly under the humidity and temperature conditions inside the Huajiang Canyon. The towers that rose from those ledges were not built with off-the-shelf materials. They were built with materials invented for this specific location. The drone that crossed the canyon first. With two towers standing on opposite sides of a 1,420-meter void, engineers faced a problem that sounds almost absurdly simple. How do you get the first cable across? In most bridge projects, a boat carries the pilot line across the water below. Sometimes, a helicopter is used. At Huajiang, neither option worked. The canyon's violent updrafts made helicopter operations in the gap genuinely dangerous. Unpredictable gusts could send a helicopter into the canyon wall in seconds. And there was no navigable water route at the bottom. So engineers deployed specialized high-performance drones to fly a lightweight pilot wire across the 420-meter gap. The drone carried the wire across, threading it through canyon wind that pushed and pulled at it constantly. Once the pilot wire connected both towers, it was used to pull a slightly heavier wire across. That wire pulled a heavier one. Step by step, the process escalated until the primary cable system was established, each stage using the previous connection to haul something bigger and stronger across the void. It started with a drone carrying a wire thin enough to hold in one hand. It ended with main suspension cables, each containing 217 individual strands, each strand bundled from 91 high-strength steel wires, compressed by hydraulic machinery into perfect solid cylinders, and sealed against moisture by automated wrapping machines. The transition from drone wire to main suspension cable is one of the most remarkable sequences in the entire project. Engineers also embedded fiber-optic sensors directly into the steel strands of the main cables during the spinning process. These sensors monitor real-time changes in internal temperature, humidity, and structural stress, transmitting data continuously to engineers who can detect the earliest signs of fatigue before they become failures. The bridge does not just carry traffic, it monitors itself. Lifting the deck from the river bottom. The bridge deck is made of 93 prefabricated steel truss segments. Combined, they weigh roughly the equivalent of 3 Eiffel Towers. Getting them into position required a cable crane system strung across the main suspension cables. A rig that lifted segments straight up from the riverbed 625 meters below. This cable crane system set a world record for the loads it handled during the Huajiang construction. But lifting the segments was only half the challenge. Each segment had to connect to the previous one with millimeter-level accuracy. A misalignment that looks small at the connection point compounds over 93 segments into a structural problem that cannot be fixed once the deck is assembled. Engineers use digital twin technology and virtual pre-assembly software to verify the exact alignment of each segment before it ever left the ground. Every piece was checked in a computer simulation first. Only when the virtual assembly confirmed perfect alignment was the physical lift approved. Major lifting operations were restricted to early morning and late-night windows, the only periods when canyon winds dropped to levels safe enough for precision work. Crews worked around the canyon's weather, not against it. The segments were hoisted symmetrically, starting from the center of the span and working outward toward both towers simultaneously. This balanced approach kept the load on the cables even throughout the assembly process, preventing dangerous asymmetric stress on the towers and anchors. Testing with 96 trucks and 3,000 tons. Before a single civilian vehicle crossed the bridge, engineers staged one of the most demanding load tests in bridge construction history. 96 fully loaded heavy-duty trucks were positioned at precise locations across the main deck. Combined weight, over 3,000 tons of deliberate stress applied to the structure simultaneously. Engineers measured exactly how the cables deflected, how the towers responded, how the steel truss segments behaved under a load far beyond anything normal traffic would ever produce. Every measurement was compared against the computer models that had been used to design the bridge. Where the physical bridge matched the model, the design was confirmed. Where it deviated, engineers investigated until they understood why. Only after the bridge passed every static and dynamic test did it open to traffic. What it changed and what it means. The journey that used to take 2 hours now takes 2 minutes. That is not a convenience improvement. That is an economic transformation for the communities on both sides of the canyon. Access to markets, hospitals, schools, and employment that was effectively cut off by geography is now routine. The Huajiang Bridge also does something American infrastructure almost never does. It was designed from the beginning to be a destination, not just a crossing. Built into the structure is an 800-meter glass elevator descending the canyon wall, a suspended glass skywalk extending over the void, a stargazing sky cafe, and a restaurant housed inside the structural cavity of the bridge towers themselves. The bridge that solves a transportation problem simultaneously becomes a tourism anchor for one of China's poorest provinces. For comparison, the Fern Hollow Bridge in Pittsburgh, a modest 4-lane road bridge, collapsed in January 2022. It had been rated in poor condition since 2011. 11 years of warnings. The repair after collapse took over a year. America's infrastructure backlog for bridges rated poor or structurally deficient runs into the hundreds of billions of dollars. China spent $300 million to build the highest bridge on Earth in 3 years, in a canyon with no roads, unstable rock, and winds violent enough to require drone pilots to cross the first cable. The canyon that separated communities for generations now has a 2-minute crossing. And inside the towers of that crossing, there is a restaurant with a view that most engineers said was impossible to reach. Subscribe and hit the bell. Drop in the comments, would you walk across a glass skywalk 625 meters above a river? Because that is now an option.